Math Day 1. We've got using buffers today. We learned what they were yesterday, the solution of an acid and its base, specifically a weak acid and its conjugate base. Remember, you have whatever acid and then the something ATE ion in most cases to give that acid-base pair. Also remember, buffers are most effective within plus or minus 1 unit of the pH when you're talking about their pKa. So I'm definitely going to need the pKa here. We're going to be using the Henderson-Hasselbalch equation 2 times. Today's goal is to use that equation 2 times to look at pH of a buffer before I add stuff to it and after I add stuff to it. So we're going to be reacting buffers with a little bit of either a strong acid or a strong base. Because remember, a strong acid will react with the basic part of a buffer, and a strong base will react with the acidic part of the buffer. So we're going to go through this today. Your practice problems do this also. So, steps to completing the calculation for adding to a buffer. Write an equation showing buffer components. Stoichiometry calculates concentration changes. I'm going to use an ice chart or something really similar to it. It's more like an ICA chart, initial change, and then after, because you're not looking at an equilibrium with a strong acid or strong base being added. So you're then going to write your equation and use the Henderson-Hasselbalch again. The question in your packet actually wants to know what the pH is before and after, which I think is pretty cool, because it shows you what buffers actually do, how little pH will change. If you think back with strong acids and strong bases, even a little bit of H plus or OH minus changes your pH a lot. So you'd expect even a dribble to cause a major pH change. So let's look at this. What is the pH after adding the acid? But first, calculate the pH of a buffer that's 0.020 molar for NH3 and 0.030 molar in NH4Cl. And then I'm going to make a change of adding a milliliter, just a milliliter. If you think of the graduated cylinders, how little that is, adding a milliliter of 0.1, so not very concentrated, NaOH, to 0.10 liters of this buffer. So the Henderson-Hasselbalch equation for the original pH, first thing you need to do is figure out which is the base and which is the acid here. And I did that. I actually wrote my base in blue and my acid in pink because of litmus paper being that way. I just thought that that was fitting, and those just happened to be the marker colors I had. I'd love to tell you I planned that out, but I looked and went, oh cool, pink and blue. So, what I have here is my Ka, my concentration of base, my concentration of acid, and the Henderson-Hasselbalch equation, which is really nice and easy to use. It's probably one of my favorite equations because everything else in this chapter is so do this step, do this step, do this step. This, I throw it in, and it works. I just calculated my pKa at 9.24 here. That's what I was fussing with my calculator over. 9.24. Great. So all I do is I plug in my values. I want pH. It's going to be equal to 9.24 plus the log. I always want to write minus log there because of pH being negative log. Be careful to write plus because we've been doing negative log so much. My concentration of base is 0.02 divided by my concentration of acid of 0.03. Now, let's see what this does. I think I have more acid than base, so I've got a bigger number on the bottom, so I'm going to have a number less than 1 for my log. Looks like I'll be a little bit below the pH on this one, and I am. I end up with the pH for this buffer system, sorry, a little bit lower than the pKa, at 9.07 when I solve this, because the log of, well, it would be 0.67, is going to give me negative 0.17 because the log, we're taking the log of something less than 1. So that's why I'm a little bit below my pKa there. This buffer would be effective between about 8.24 and 10.24. Sounds great. So Writing my equilibrium equation for the addition of the strong base to the weak acid. Okay. So I'm just going to do this. I'm going to take out that round of Henderson-Hasselbalch and leave the other stuff up there. So what I've done with this buffer, and you have to realize NH4Cl is going to break down into NH4 plus and Cl minus. And we only really want the NH4 plus. Why does it break down? Group 17 with ammonium, which is +1, soluble, strong electrolyte. So I'm going to end up with NH4 plus reacting with the OH minus that I got. I'm not even going to write the H2O in this because I'm heading for an equation here. That's going to give me, I guess I will. I'll be chemically complete. We'll throw it off to the side. Like, there's liquid H2O. Isn't that nice? But what else did I make here? When I gave up that hydrogen, I've made the weak base from the buffer system. I've converted the acid from the buffer system into the weak base. That's cool. So this can get a little sticky if you use concentrations. So it's easier to do with moles, honestly. So in the packet, I have my mole calculations. Since they're 0.1 liter each, it basically just moves the decimal. What I'm going to set up is a chart, like I said, kind of like your ice chart, but it's more like ICA, because it's like initial. And I am going to change it, but it's not going to be really equilibrium. It's more going to be like after. If you label it equilibrium, I'm not going to care, and water does nothing. I'm not going to be mad at you if you call it equilibrium, as long as you do your math right. So what do I start with? My initial concentration of NH4 plus, well, I converted it to moles, so I went 0.0030 moles. I didn't start with any OH, I had to add it, and I go to 0.0020 moles right from here. Because I've given you volumes, you can go from molarity to moles. Great. So my change, what am I doing here? My addition of OH is a tiny, tiny amount. I'm adding 0.1 molar and 1 milliliter of it, which should still really blow up the, well, I should say blow up, drag down, it's OH? Yeah, blow up the pH. It should make the pH go up a lot. That is the definition of a base. So, I'm only adding 0.0001 moles, but I'm expecting that concentration to go up. Here's where this is different than an ice chart. You have to think, am I adding or subtracting? This reacts with this. So in this case, I'm taking away 0.001 moles, 0.001 moles there, because it reacts out. In an ice chart, it goes the same direction. In this case, I'm going to subtract from my NH4 plus, and I'm going to make NH3. So I'm going to end up here with 0.0029 moles, because I've used up some. E's gone. OH is gone. The NH4 plus ate it. It's gone. It's this now. And that's going to be 0.0021 moles. Now to do this next part, we have to, I don't want to say assume, we have to have faith that we haven't blown out the buffer. We haven't exceeded the buffer capacity, that the buffer is able to cope with this small change. I'll tell you that if you have a teacher that asks you a question where you have to guess if it blew out the buffer, your teacher is rude. I would expect if I'm asking you if this works as a buffer or telling you to calculate the pH after, that the buffer is functioning well with this amount. So, I'm going to use the Henderson-Hasselbalch equation again. I'm going to do pH equals pKa plus my log, and I can use moles here. Here's why. They're in the same solution. So they're going to be divided by the same volume. It'll cancel out in the equation anyway, so feel free just to stuff your moles right into the equation. Where'd they go? Here we are. NH3 is my base, so it's log of base over log of acid. You'll see that the change was not very big because it was 0.002. It was 0.02 over 0.03. It's real close to the same now. 9.24 plus log, comes up in parentheses, 0.0021 divided by 0.0029. Did I get something different? Of course I did. Of course I did. Now, if you remember, at the beginning, I think we were what? What was our first pH? 906 or something? 907. 9.07 for our pH to begin with. When I calculate this out, I get 9.10. It did go up. I added a base. That makes sense. But it sure didn't go up like if I had thrown that much sodium hydroxide into water. The buffer buffered. It did its thing. It reduced the pH change by allowing the strong base I added to react with a weak acid and just produce more of the weak base, which was already present. So you get a really small pH change, and you're still able to use the Henderson-Hasselbalch equation to prove that. So, you got practice on this. If you were adding an acid, you would have the acid react. Let me get this in before I quit. If you were adding an acid, and I'm just going to throw this in here, maybe in a different color. If I had added an acid to this buffer system as an afterthought, an acid would be able to react with that NH3 plus and instead give me NH4 plus. So that would give me this side back if this buffer were to neutralize an acid. Just throwing that out there. I think that'll help you on the homework today. See ya.